Welcome to this video lecture on the Navier-Stokes equations. This is just an introductory lecture. I have a different set of lecture videos that go into the Navier-Stokes equations in more detail. So this one is just an introduction, just describing what the equations are, where they come from, why we're interested in them. But if you want more detail on how to use the Navier-Stokes equations, there's some bonus material or other video lectures that I encourage you to take a look at. So let's go ahead and get started. Take a look at their screen here, and what you'll see is a schematic on the top. This is a schematic of a dorm room, a college dorm room, and a postdoctoral researcher and another colleague of mine and I were curious about the spread of COVID within a dorm room. So this is active research. We haven't finished it yet. We're actually in the process of still studying it. But the way we're studying it is basically the question is this: if we have a dorm room with two students and there's an air purifier, how effective is the air purifier at clearing respiratory droplets from the air? Right. So COVID is a respiratory disease, and it's transmitted through exhaled droplets that other people inhale. Right. And so we wanted to see where those droplets end up in a dorm room. So what we have is this dorm room here. This is actually a typical Purdue college dorm room. You can see the entryway over here. There are a couple of desks. We have a lofted bed, a couch, a non-lofted bed, a little nightstand, and then we have an air purifier. This is a HEPA. That's a high efficiency, I can't remember the exact acronym, but it's basically a high efficiency filter to remove particulate matter, droplets being particulate matter. So we have a HEPA filter here, and we put it in two locations. So one location was here, and then another location was next to like in between the nightstand. So the idea was, if you had two people sleeping in the dorm room at night, and you can imagine the people here, the red arrows are where the person's head would be, and the arrow indicates the direction of exhalation. So when they exhale, that's the direction of where the drops would go initially. And you can imagine that somebody might put the HEPA filter over here and between the couch and the nightstand, just to keep it out of the way so you don't trip on it. And then another place where we put it was right in the middle of the room, which we thought would be an interesting location, just more centrally located. And what we then did was model the airflow in that room using the HEPA filter, and that's what this picture is on the bottom. What you're seeing, it's kind of a mess, but you're seeing velocity vectors for the flow field in the room, with the color corresponding to the speed. So dark blue is a slow speed, and red is a high speed air. So these are in meters per second. So you can see, so here's where the non-lofted bed is, here's the lofted bed. These big arrows are just kind of the general flow field orientation, so the circulation pattern. So the way this HEPA filter was designed is you pull in air from the bottom, and then it filters it, and then the air goes out through the top, and you can see it impinges on the ceiling and then circulates back around and then back down into the air filter ultimately. So we modeled the flow field in this room, and then what we did is we injected droplets from where the people's faces would be, and then watched where those droplets ended up. So unfortunately, and I feel a little bad about this, but I don't have the results to show you just yet because it's ongoing research. But our preliminary results are that it's the filters aren't exactly as good as you might think. What ends up happening is, because the flow is directed upward, and by the way, these HEPA filters, we got the characteristics from just a popular online storefront, so basically Amazon.com. We looked at some HEPA filters and got characteristics from those and then modeled them here. And what ends up happening is any droplets that are exhaled actually get lofted into the air from this HEPA filter, and they stay lofted for a while. They eventually, some of them work their way through the filter and get filtered out, but most of the droplets end up actually collecting on surfaces in the room. They don't actually make it through the filter. They float in the air for a long time, and then they get deposited on the walls or on the floor or on the bed surfaces and things like that. Very small fraction actually make it through the filter, but many of the droplets actually stay suspended for a long period of time because of the airflow that's directed upward. It just kind of keeps the droplets in the air. So they're not as good as you might think, at least based on our preliminary research. I need to qualify this by saying we're not done yet. So we're still studying the problem. So we intend to publish a paper once we get the final results and see what it looks like. But anyway, the reason I'm showing you this is because the way that we get this flow field in this research is through a technique called computational fluid dynamics, or CFD. And CFD is essentially solving the equations of fluid mechanics numerically. What equations are those? They're the continuity equation, which is just conservation of mass in very small control volumes. So we've covered the continuity equation in a different video. So just conservation of mass, that's one equation. And then the other equations are the momentum equations for Newtonian fluids. So we're modeling air, which is a Newtonian fluid, and the momentum equations are just Newton's second law, but they're done for very small control volumes. And when we do the momentum equations for a Newtonian fluid, those are called the Navier-Stokes equations. So it's just Newton's second law for a Newtonian fluid. So it turns out with the continuity equation, or conservation of mass, and the Navier-Stokes equations, which are just Newton's second law for a Newtonian fluid like air, that's enough equations for our incompressible fluid mechanics system here to allow us to solve for the velocity fields. Now, you can't do those by hand very easily. There are only a few special cases you can solve by hand with the Navier-Stokes equations, but you can do it with a computer. And so that's what we did in this research, is we had a computer solve those equations for us. It's time-consuming, a lot of number crunching going on, so you need powerful computers, but you can still get a pretty good representation for the flow field. So since we're solving the Navier-Stokes equations, I thought that would be a good motivation for the topic today, which is just an introduction to those Navier-Stokes equations. So let's go ahead and get into the material. And I guess I already covered this first question. What are the Navier-Stokes equations? They're really just the momentum equations, or just Newton's second law, for a Newtonian fluid. Specifically a Newtonian fluid, one where the shear stress is proportional to the velocity gradient, right? So that air and water are examples of Newtonian fluids. And by momentum equations, what I mean by that is just the linear momentum equation applied to a very small control volume. Okay, so I'm gonna show you the momentum equations in a moment, and then we'll plug in our Newtonian relations. That's called a constitutive relation. It just relates the shear stress to the velocity gradient. And then we'll end up with the Navier-Stokes equation. So that's what we're going to end up doing here in just a moment. So if you look at the screen here, you'll see the derivation. What we're going to do is we're going to take a look at a very small control volume. Oops, let me erase that. We're going to look at a very small control volume. It has a width dx, height dy, depth into the page dz. Here's our coordinate system, and then we're going to apply the linear momentum equation, which you're all very familiar with by now, and apply it to that little control volume. And just to keep things a little simple, I'm only going to focus on the x direction in this derivation. You can do the same thing in the y direction, in the z direction, or you could do it in cylindrical or spherical coordinates, whatever you want. But for simplicity, just to give you an idea of the concept, we're just going to focus on the x direction. So you can see when I wrote the linear momentum equation here, we're only working with the x component. Okay, so this is the time rate of change of x linear momentum within the control volume. This is the x momentum flux out of the control volume. There are the body forces in the x direction. There are the surface forces in the x direction. And we're going to apply it to this control volume. Now the arrows I've drawn in here, these are the flow directions. So it's coming in from the left-hand side, out through the right, in from the bottom, out through the top, in through the back, out through the front. So what we're going to do is first analyze the time rate of change of x linear momentum within the control volume. So that's this term right here. And if I apply that to our particular control volume, here's our ddt term. Notice it goes from an ordinary derivative to a partial derivative. It's just a little math detail. It has to do with the fact that this control volume could be located anywhere in xyz space. And since it's located anywhere, it means it could be a function of what's happening in the control volume, could be a function of position as well. So that makes it a partial derivative. Anyway, so that's a math detail. But we have the x velocity right here, density right there, and then the little bit of volume is just dx, dy, dz. That's just the volume of that little sort of rectangular cube. When you take the derivative of this, I'm going to assume that we're dealing with an incompressible flow. And I should probably, I'll put in here for Newtonian, incompressible Newtonian fluid. The form that, well, you know what? let's keep that off of there. The form that we're going to derive is for an incompressible fluid, but you can still write the Navier-Stokes equations for a compressible fluid as well. But in my derivation, I'm just going to focus on the incompressible part. So since it's incompressible, the density comes outside the derivative. The volume, dx, dy, dz, it's just a fixed volume, so that's not a function of time, so that comes out. So the only thing that the time derivative acts on is the x velocity. So that's our first term right here. Now the second term gets a little more complicated. It's just, the concept is easy, but there's just more bookkeeping you have to do. So this is the net flux of x linear momentum out of the control volume through the sides. Okay, so what we're going to do is just rewrite this. The term in parentheses there is just the mass flow rate. So I'm just going to write it as mdot. And there's our ux. And then I'm going to do this over all the sides. Since this integral is over the whole control surface, it's really just our sides here. So I'm just going to rewrite it that way. It's just a little easier, I think, for you to understand it in that form. So what we're going to do is focus on first on in through the left. So there's my mass flow rate. There's my ux right there. And the way we're going to write this is we're going to use this Taylor series expansion idea that we talked about very early in the course. We're going to say that the mass flow rate times the x velocity at the center, so right here, we're going to say that we will start from that point, and then by starting there, we'll move off to the left and see how that momentum flux changes. So we're going to start at the center. There's our momentum flux in the x direction at the center, and then we're going to move to the left over here, and then we're going to see how that momentum flux in the x direction changes with respect to x, because we're moving from the center off to the left, which is in the x direction. So that's how it changes. That's the gradient in the x direction, times how far we've moved to go from the center to the left. So we start at the center and we move off to the left. That's a distance of a minus 1/2 dx. So that's where that comes from. So this is just how that momentum flux changes in the x direction times how far we've moved in the x direction. So it's the momentum flux that we start with plus how much it changes as we move to the left. And that gives us the momentum flux in through the left side. We can do the same thing on, let me continue. What I did in this next step is just expand out the mdot. So the mdot is just the density times the velocity times the area through which it flows. The area over here is dy times dz. Let me just highlight it. It's just this area right there. So that's where the dy dz comes from. So mdot is just the density times the velocity in through the left, which is the ux. I'm sorry. Yeah, this is the mass flow rate. The mass flow rate, I should say, at the center is the density times the velocity in the x direction times dy dz. And then there's our ux right there. And I just did the same thing over here for mdot there. And then if you simplify that, you'll see we can go from this line to this line by just expanding out here. You have two ux's, they're right there. And then I took the dy dz and multiplied it by the dx out here. Okay, so just a little bit of algebra for that step. We can do the same exact idea out through the right-hand side. So that's what this next line is. The difference for that is when we go from the center to the right here, we're going a distance of a positive 1/2 dx. So that's where the positive 1/2 dx comes from here. We can do the same idea for the top and bottom. So here's the x momentum flux coming in from the bottom. So the mass flow rate coming in from the bottom would be a rho times a uy times dx dz. That would give you the mass flow rate in from the bottom. And it contains with it some x linear momentum. And then when we move from the center to the bottom, we're moving in the y direction, so that's why we have a partial derivative with respect to y. And to go from the center to the bottom, it's a distance of a minus 1/2 dy. So that's where that minus 1/2 dy comes from. So I think you get the idea. We just repeat this for the bottom, top, back, and front. And that's what all of these various terms are. And then what we're going to do to get the total momentum flux out is we're just going to add them all together. Okay, so that's what this term is the net x momentum flux out of the control volume through the surfaces is just adding all of these terms, everything here, just added together, and then simplifying, and that's what this is. So it simplifies down to something that looks a little better. So now we've gotten the this term taken care of in the x direction. Now let's go ahead and do the body force term and the surface force term. So the body force term is pretty simple. It's just going to be, let me go back up to the picture. Body force on this cube is just going to be the mass of the cube times the gravitational acceleration in the x direction. I'm only worried about gravity when I derive this. So that's just here. Here's the density times the volume. That gives me the mass, and then there's gravity in the x direction. So that's the body force term. Now the last term is the surface force term. That one gets more complicated again, and so I'm going to show another picture. Here's our cube again, our coordinate system. And what I'm going to do is just show the surface forces written in terms of stresses acting on all the various surfaces. Okay, so we're doing this in terms of stresses. So for example, on this right face, the force in the x direction is due to a normal stress on that surface. So that would be like a sigma xx. Okay, so if you remember from your strength of materials, the stress sign convention is the first subscript is what face you're on. Okay, and that face is the face with a certain normal vector pointing in a certain direction. So the normal vector on this face points in the x direction. It's an outward pointing normal vector. And then the second subscript is the direction of the stress, right, or the traction vector. So this would be on an x face pointing in the x direction. And then up here on the top, this would be on a y face because the normal vector is pointing in the y direction. So it's on a y face pointing in the x direction, and then the front here would be on a z face pointing in the x direction. And then we have corresponding stresses on what we call the negative faces. The negative faces are ones that have normal vectors pointing in the negative direction. So this would be on a negative face back here because the outward pointing normal on that face points in the minus x direction. And the stress on that would also be a sigma xx. Same sort of thing with down here. This would be a sigma yx and a sigma zx. Okay, so anyway, that's the stress sign convention. But just like what we did with the momentum flux, what we're going to do is state that the stress state at the center of the cube is just like sigma xx and sigma yx and sigma zx. But then when I'm going to move to the right-hand side, so that stress changes, I'm going to use my Taylor series approximation. So the stress there is sigma xx plus how the stress changes as I move in the x direction, multiplied by how far I moved to get from the center to this face, which is a distance of a positive 1/2 dx. Similarly, if I go from the center to the left face, there's the stress I start with. This is how the stress changes as I move in the x direction, and then here I moved a distance of minus 1/2 dx. And you can do the same thing for the top and bottom faces, and then the back and front faces. Okay, I didn't write out all the stress, like the stress on the bottom face and the back face. It'd be too much writing on the screen. It's just kind of messy. So those are how the stresses in the x direction look like. And to get from a stress to a force, you just multiply by the area over which that stress acts. So, for example, the normal force on the left face would be the stress on the left face. That's this one. Multiplied by the area of that face. That area is just this area, which would be a dy times a dz. That's right here. And then here's the normal stress on the right face, right there. So there's that normal stress multiplied by its area. You can do the same thing on the bottom face. Notice that the area on the bottom is different. It's dx times dz. There it is on the top face. Shear force on the back face, shear force on the front face. So these are all of the forces acting on the surface of that cube in the x direction. And that gives us our surface force in the x direction. And we can simplify that. And if you go through all the algebra to simplify it, it comes out to be something relatively straightforward as well. So now we have all the terms we need for our linear momentum equation. Let's go ahead and substitute them in. So what we're going to do is take all of our components, substitute them back in to our linear momentum equation, and then simplify it. So when we do that, so we substitute them all together. There's our linear momentum equation. You can see there's a dx, dy, dz in all of these. So we can divide through by that, and then we end up with the linear, this is called the momentum equation in the x direction. So that's our momentum equation in the x direction. It's just linear momentum applied to a small control volume. It's just really Newton's second law applied to a small control volume. And you can see we have terms like, density and velocity. Now, if we're dealing with an incompressible substance, then the density, of course, just can be written outside the brackets there. But we have, velocities and stresses. It'd be nice if we could rewrite this expression so it's all in terms of velocities. If you think about like a Newtonian fluid, we have an expression that relates stresses and velocities. So it'd be nice if we could substitute that into this equation and simplify it further. And we're going to do that in just a moment. But here's the momentum equation in the x direction. If you go through the whole procedure again, you can do it in the y direction. You get that expression. Do the same thing for the z direction. You get that expression. So again, remember the linear momentum equation is a vector equation. So you have an x, y, and a z component. Okay, so those are the momentum equations. But like I said, it'd be nice to be able to express the stresses in terms of velocities, just like what we do for a Newtonian fluid. So that's our next step. We're going to use what's known as a constitutive relation. A constitutive relation just relates various quantities together. Like the ideal gas law is a constitutive relation because it relates pressure, density, and temperature. If you remember early in the course, we had this expression for finding the shear stress for a Newtonian fluid, right? This is a constitutive relation. It relates the shear stress on a y face in the x direction to the velocity gradient. This is the x velocity and how it changes as you move in the y direction. That's a Newtonian constitutive relation. Now this is a very simplified version. It turns out that for a Newtonian fluid, you can relate all the various stresses to the velocities, and it's a little more complex than what we had here. So what we showed you earlier in the course was just a very simplified version. The full relationship for a Newtonian fluid is this set of equations. Okay, so this is the full version, and you can actually derive this, but it's outside the scope of this course. So just accept it as a fact here. If you want to know more about it, you can actually take a look at my book style notes, and I will go into more detail on where it comes from. But if you look at this for a second, this tau yx equals mu dux dy, that's actually this expression right here. Let me highlight it. So there's I've written everything in terms of sigma rather than tau here. But there's our shear stress on the y face in the x direction. There's your dynamic viscosity, and there's your dux dy. Now, you can see that the real expression actually has an extra term in it. There's a plus du dx. We never really dealt with that before because in our previous examples, the uy term was always 0, so that term never showed up. But in general, there's actually this extra term that you have to factor in. But you can see we have an expression for the normal stresses up here as well as the shear stresses. So we can take those expressions, substitute them all back in up into our momentum equations for the various sigma terms, and then simplify it. And we can go ahead and do that, and I'll save you all the algebra, but trust me that when you go through and do it all, you end up with the following set of expressions right here. So these are the momentum equations specifically for an incompressible Newtonian fluid. I've assumed that the viscosity is constant, so it doesn't vary with any of the gradients. And when you do all that, you end up with what are known as the Navier-Stokes equations. And that's the set of equations here. Here's a Navier-Stokes equation in the x direction, in the y direction, and in the z direction. Okay, so the Navier-Stokes equations, again, are just the momentum equations for a Newtonian fluid, and in this case, I did it for an incompressible Newtonian fluid, one with where the dynamic viscosity is a constant. So just to kind of show you what the various terms are, I mean, when you look at this, it looks really complicated and messy, and they're don't get me wrong, these are tough equations to solve, but conceptually, they're actually pretty simple. The terms on the left-hand side are the following. So this term here, the dux dt times the rho, that's your time rate of change of x linear momentum in the control volume. That's the ddt term in the linear momentum equation. The next set of terms with the ux, dux, dx, etc., those are your linear momentum flux terms through the sides. So coming, in and out through the left and right, and top and bottom and front and back. So that's your x linear momentum flux set of terms. The rho gx, that one's pretty straightforward. That's just your body force term. And then this last one, those are your, oh, you know what? I forgot a term in here. How wrong of me. We need to put these in here as well. Actually, there should be a minus. So there was your body force term. Then these terms here are your surface force terms. Okay, so these are your net shear stress forces or shear forces acting on your control volume. And then this is your net pressure force acting on the control volume. Apologize, I forgot those. I'll fix those in the lecture notes that I post. So that's all it really is for your Navier-Stokes equations. Just basically Newton's second law, F equals ma, but applied to a control volume. So it's our linear momentum equations. And then we just made use of our Newtonian constitutive relations. So it ends up to be kind of complicated looking, but conceptually it's pretty straightforward. It's just really kind of a momentum balance. And again, because we're dealing with the momentum equation, you have an x component, a y component, and a z component. Okay. So how do we use this set of equations? Okay. So we'll combine these. So if you combine these with the continuity equation, you actually have a set of 4 equations with 4 unknowns. The unknowns are the velocity components, ux, uy, uz, and the pressure, p. Those are your 4 unknowns. The density, presumably you would know because you know what fluid you're dealing with and it's incompressible. Similarly, you know gravity and you also know the dynamic viscosity. It's a material property, so you could look it up. So 4 equations, 4 unknowns, then you could presumably solve those. The challenge is that solving these equations is pretty difficult. A more mathematical way to describe these equations is they're a set of coupled nonlinear second-order partial differential equations. Coupled because you see there's a ux, for example, in each one of these equations, so they're coupled together. Same with like the pressure, for example. Partial differential equations because they're all partial derivatives. Second order because they're the highest derivative here is second order, and nonlinear because you have terms like a ux times a ux here. So that's mathematically kind of more. Pragmatically, what it means is that the equations are really tough to solve. And it turns out there are only a handful of actual analytical solutions. In general, we don't know how to solve these equations by hand. And so that's where the computational calculations come into play. You can approximate these equations numerically and then have a computer help try to solve them for you. It's still very challenging. There's a lot of math involved in that and numerical challenges, but it's doable. And certainly if you have a very powerful computer, you can get better and better approximations to the real equations. So that's what computational fluid dynamics really comes down to, is trying to solve these equations with the continuity equation numerically. And I've shown them here just for incompressible flows, but you can do the same idea for compressible flows as well. So how do we use these equations? First of all, as I mentioned, there are some simple cases you can actually solve by hand. There's just a handful of them, but you can do some, one of which is like a Couette flow. We've talked about this in the course before, where you have a fixed bottom boundary. Top boundary moves at a velocity capital U, and if you recall from earlier in the lecture, we said that the velocity profile for this situation is linear. Now, we just gave that to you, but it turns out you can actually derive it. You can prove it. And the way you can prove it is by solving these Navier-Stokes equations with certain assumptions. The assumptions you have to make are, gravity acts only in the y direction here, that the plates are infinitely long and parallel to one another. It's a steady flow. Things like that can help. It's planar, so it's the same kind of picture in and out of the page. If you make all those assumptions and you simplify the Navier-Stokes equations and the continuity equation, you can end up with the linear profile. So you can solve these equations for very simple cases. Another one that's very common and very helpful for us is flow in a circular pipe. You can show that the velocity profile there is parabolic. We use that as a fundamental velocity profile for pipe flows, for example, laminar pipe flows. So we can use the Navier-Stokes equations for some very simple cases, and those simple cases can serve as models for real complex systems. So that's what I mean by how we use these equations. We can use them for engineering models because we can use those special cases as approximations to real life situations and then use the velocity profiles and pressure, et cetera, that we get from the Navier-Stokes equations to solve those real engineering problems. So we can use it as engineering models, and it's done all the time. So it's specifically the two most common would be this Couette flow, and this is known as a Poiseuille flow. Let me write that out, Couette flow. And this one will come back to Poiseuille flow when we talk about pipe flows. So that's one way, and a very common way to use the Navier-Stokes equations. Very, very common. Another way that we use it is to verify computational models. So we said that you can solve these equations numerically using a computer, and that's computational fluid dynamics, or CFD. But when you write a computer program, you want to make sure it's working properly. So how do you double check that you're doing all your computations correctly? You haven't, coded in a bug or something like that, right? So one way you can verify your CFD code is to compare your numerical solution to a known analytical solution to the Navier-Stokes equation. So for example, we know what that velocity profile looks like in the Couette flow. We can solve that analytically with the Navier-Stokes equations. So then you use your CFD computation to solve for the same velocity profile, and you just double check that it matches. So it's a way to verify your CFD code, and once, if your CFD code matches the analytical solutions, then you have confidence that it's going to work for other more complex cases. Okay. And then lastly, this one's a little more abstract, but by looking at these equations and analyzing the mathematics of it, it can provide you a deeper insight into fluid mechanics and the mathematics of fluid mechanics. Just more fundamental understanding of what's happening physically or mathematically with the equations. I won't get into that too much, but it's if you have the set of equations to work with, you can dig into those and understand things better. If you don't know what equations you're working with, it's hard to understand them at a deeper level, right? But when you do know the equations, then you can start to dig deeper mathematically and get just a better appreciation and understanding of what's going on fundamentally. Okay, so that's basically all I wanted to do to give you an introduction to the Navier-Stokes equations. At the undergraduate level, I don't think my personal philosophy is doing a lot of solutions to the Navier-Stokes equations at the undergraduate level is not really all that necessary. I have colleagues who disagree with me. I just know that when people graduate with a bachelor's level degree and go out and work in industry, they're not solving many Navier-Stokes equations by hand. It's just not a common thing that people do. But it is good to get an introduction to it because computational fluid dynamics, which many people who go into fluids in industry will use, is based on these Navier-Stokes equations. So you should at least have some exposure to them and understand where they come from and how they're used. Now, when you get to the graduate level, you will end up solving Navier-Stokes equations by hand, and it's certainly worthwhile. If you are interested in that topic, like I said at the beginning of this lecture, I do have a set of other lecture videos that go into the Navier-Stokes equations in more detail and actually do solutions by hand. I do some examples where I go through some of the solutions that you can do by hand. Okay, I'll go ahead and end it there. Hopefully you have a better appreciation for what the Navier-Stokes equations are, and they seem hopefully a little bit less scary. We'll end it there.